good morning, everyone. How did your homework go? Any questions about the homework? Okay, 72 and 73. Right, so we have a look at 72. Okay, we have the function y equal. Usually I don't do, if two problems are similar, I will pick one of them. So it's 4 sine x cosine x. And the question is, find an equation of the tangent line to the following curves at the given value. Okay, so we have to find the equation of the tangent line. Right. So to do that, first we find the derivative. So we have to find the equation of the tangent line. First, we have to find the derivative because the slope is the value of it at pi over 3. So this is a product. So watch carefully how I wrote it. So that's 4 sine times cosine. So we use the product rule. Is equal to 4 is a constant. The derivative of sine is the cosine times the cosine plus 4 sine x. The derivative of cosine is minus sine. So I will get 4 cosine square x minus 4 sine square x. So that's y prime. Now I needed the slope of the tangent line at pi over 3. So we need now to find the slope of the tangent line. This is the value of the derivative at pi over 3. Means I plug in pi over 3 for the x. So this is equal to 4 times the cosine square of pi over 3 minus 4 sine square pi over 3. So now we have to remember what's the cosine of pi over 3. Now remember, cosine square is nothing more than the cosine of pi over 3 to the power 2. That's the definition. And this notation means the sine of pi over 3. Okay, so now cosine pi over 3, those are something we should know, is a half squared minus 4 square root of 3 over 2 square. Okay, so finally I would get 4 times 1 over 4 minus 4 times 3 over 4. So I end up with 1 minus 3, which is minus 2. So this will give me the slope of the tangent line. Now I need a point. So that's the slope and the point. So the slope is minus 2. The point is the point on the curve. So it's pi over 3, f of pi over 3. The function f at pi over 3. Because whatever, so we need the tangent to the graph. So I need to know at pi over 3 what's value the function take. So this is pi over 3. And f of pi over 3 is 4 cosine pi over 3 sine pi over 3. Okay. So it's going to give me pi over 3, that's the point. And cosine pi over 3, that's square a half. So let us compute f of pi over 3 here. This would give me 4 times cosine pi over 3 is a half. Sine pi over 3 is the square root of 3 over 2. So if I multiply those out, I will end up with the square root of 3. So the equation is, the tangent line is y minus the square root of 3 equal minus 2 x minus pi over 3. Okay, so be very careful. The point is pi over 3 and the function. Now here the derivative, it's not the derivative at pi over 3, it's the value of the function itself at pi over 3.
I have a question.
Please go.
All right, so you multiply 4 by 1/2 and square root of pi over 2 because they were the ones in 4 cosine pi over 3, correct? Is that equation right there?
This one?
Yes.
This is what the function, initial function is. F of x.
Okay.
F of x. Remember, here I need the function at pi over 3. It's 4 sine x cosine x. That's
All
the
right,
function.
so you just plug it in?
You should plug in pi over 3 into the expression of the function itself, not the derivative anymore.
Okay.
Is that clear? The function itself.
Yes.
Because this is the point on the graph of the function. So now, if I go back here, this is pi over 3. The output is, so this is the function. That's the square root of 3. Okay. And the slope is -2. It means that's the tangent line. That's nothing more than the tangent line. But the function, I know that it goes through this point, and this is the tangent line. So it's going to look something like that. That's how or the other way. I don't really know exactly. That's how the function should look like, either below the graph or above the graph. That's intuitively how the function should look like. Okay. Now you can graph the function, and you should do that. Graph the function. It means graph this. Graph the tangent line. Okay, you can use decimals, which is very good tool. Graph both, you should have this picture. Exactly. Of course, the function will finish, but that's what's going to happen at the point pi over 3 square root of 3. That's how the picture should look like. All right? Any questions?
All right, sounds good. Thank you.
Now, 73 is verbatim the same. So I will not do problems which are exactly the same. You guys will do number 73. It's verbatim. It's different function and find the derivative. Okay, now let's look at 41, and then I go back to the other one. Okay, so that's a typical quotient rule scenario. So it's 1 minus cosine over 1 plus cosine. Okay, so that's the quotient of two functions. This divided by that. So we have to use the quotient rule. There is no way out to compute the derivative. So the derivative is the derivative of the numerator times denominator minus the numerator times the derivative of the denominator. So that's and the whole thing by the denominator square. Okay. All right. So now the rest is finding each derivative by itself. So this would give me. So this is 1 plus cosine x squared. And now, derivative of 1 minus cosine. The derivative of 1 is 0. Minus derivative of cosine is the minus sign. I will have that times 1 plus cosine minus 1 minus cosine times derivative of 1 is 0 plus derivative of cosine is minus sign. Now we just simplify a little bit, and if we can combine, we do. If we can't, we stop. So minus is going to give me plus the sign, and I multiply. So plus now times that's going to give me the sine of x plus sine x times cosine. Here I have a minus, and we have to be very careful. A lot of you, as I said before, are not paying attention when they are distributing a minus sign, and they are getting you into a lot of trouble. I have a minus here and a minus here, which give me a plus. So I will have plus the sine x minus sine x cosine x. So be very careful when you distribute. So plus and minus basically cancel each other out, and I will be left with 2 sine x over 1 plus cosine and of the problem. Okay. Never distribute the denominator if it's square. So if the denominator is like this, never distribute it. You just keep it to the power 2 and end of the problem. All right, let's look at the last 2 problems and then we move on. So 76. Location of the tangent, whatever. For what value of x? So we have the function g of x equal x minus sine x. And the question is, for which value of x is the tangent line horizontal? So we should be able to sketch the function. I think this function is going to look, we'll sketch it in a second, something like that. I think so, I'm not sure. And the question is, when is the tangent line horizontal? It means we're looking at where the function is peaking, basically, or having values, those points. And so we have to set g prime equal to 0 and solve for x, because we're asking where the tangent line is horizontal. That's really the question. Okay, so we're going to set g prime equal to 0. So what's g prime? It's 1 minus derivative of sine is cosine. So we're going to set g prime of x equal to 0. So this means that 1 minus the cosine equal to 0. Means the cosine of x is equal to 1. And now the question is, when is the cosine equal to 1? For which values of x is the cosine equal to 1? So let us a little bit remember the graph of cosine. How does it look like? Start here, goes down, back up, goes down, back up, goes down, back up. And that's the graph of cosine. So what is the cosine equal to 1? At 0, at 2 pi, 4 pi, and back here, minus 2 pi, and so on and so forth. So cosine x equal to 1 for x equal 0, plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, and so on and so forth. Would it be minus cosine? Yeah, minus cosine equal minus 1. Means the cosine equal plus 1. All right? Jess, I don't understand the question. 1 minus cosine x equals 0.
Oh no, never mind. You just explained it. That it still equal cosine x equals 1. Okay.
Okay, all right. So x equal to this, so that's where the value of x. Another way to write this is x equal, if you can keep it like this. Another way is 2k pi. Why 2k pi? Because every is 2 pi, 4 pi, 6 pi. We can basically summarize this by writing 2k pi, where k is an integer. K is an integer. So the slope is horizontal for all those values. So 0, 2 pi, and so on. So if we graph the function a little bit, let me try to share the screen and graph it. Okay, so this is my decimals here. And my function is x minus cosine x. And this is nonsense. And okay. Somehow my scale is totally out here. So I can go 10 and minus 10. And I'm changing the scale on my input, so I'm gonna go 20 and minus 20. Okay. So basically what we're looking for are, no, I need that. What we're looking for, so is this point right here. So the graph is not very good. So I would like to change the graph tiny bit. Minus 5 and 5. Okay. So we're looking for those point. So these are the point that we actually are interested in. So this point right here, this point right here, this point right here, this point right here. These are the point we are interested in. Those are the plus or minus 2 pi, plus or minus 4 pi, and so on and so forth. Okay. All right, now part A is the following. For what value of x is the slope equal to 1? So we're going to find the values of x where the slope of the tangent is 1. It means we want to find the values of x again when the derivative is equal to 1. Okay, and we've computed the derivative already. So the derivative is 1 minus cosine. So we're going to set 1 minus cosine equal to 1 and solve. 1 and 1 simplify. I will get 1 minus cosine x equal to 0. It means the cosine of x equal to 0. And now, which value of x would give me a 0 for cosine? We get back to our graph of cosine, and we always remember how the graph looks like. The cosine is crucial that, we know the graph of sine and cosine. We have to think through them and the definitions. So this one. So the cosine, so that's the cosine of x here, is equal 0 at pi over 2, 3 pi over 2, 5 pi over 2, and so on and so forth, minus pi over 2, minus 3 pi over 2. Okay, so cos x equal is going to be plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, plus or minus 7 pi over 2, and so on and so forth. So at those points, the slope is equal to 1. Okay. Right. Well, I'll have a look at 77, and it's verbatim the same. I actually will drop it. It's actually the same idea, so I'll have a quick look at it, and then we proceed. So number 77. We have the function f of x equal x minus 2 cosine x. And the question is again, when is the slope, when is the tangent line horizontal? Okay. So it's the same idea. We're going to set f prime equal to 0 and solve because they want it to be horizontal. They're not asking for the slope of the tangent in here. So f prime is 1 minus 2. The derivative of cosine is minus sine equal to 0. Means 1 plus 2 sine x equal to 0. So which will give me, okay, we can solve for sine. Sine x is minus a half. And now the question is, for which values of x is the sine equal to minus a half? So we can go back here a little bit to our unit circle. That's my unit circle. And I want the sine to be minus a half. So the sine is the y coordinate. So that's minus a half. So I'm after this angles here. Now I use my reference one. Of course, my reference one is right there. So that's the reference one. And we know that if the sine is a half, it means this has to be pi over 6. So now the angles we're looking for are, one is, so we have two set of angles. We want this one. This is this one right here. That's the pi plus pi over 6, which is 7 pi over 6. So we will have here 7 pi over 6. And now the other one that I will make it in purple. I don't know if it shows purple for you. So this is the big one. And this one is 2 pi minus pi over 6. It means 12, 11 pi over 6. So the other angle is 11 pi over 6. And now we know that the sine doesn't change if we go around the circle a full rotation. So we can take 7 pi over 6 and then 7 pi over 6 plus 2 pi. 7 pi over 6, actually plus or minus 2 pi. Nothing will change. Plus or minus 4 pi. And so on and so forth. And the same thing will repeat here. So it's 11 pi over 6 plus or minus 2 pi. But they don't tell me which one they want. So we have to get all of them. Okay. And that's how we do it. So that's where so when we sketch the graph of this, and we saw peaks and valleys. So when we graph and start functions having a peak, then it has a valley, then it has a peak, and it has a valley, something like that, we should know when those peaks and valley are occurring. That's really the values we are picking up from there. All right. Okay. Now we're going to move to section 3.6, which is a section that we've seen before, but it will give us a break for today from the rules, and tomorrow we go back to the rules of differentiation. So as I said, it's something we've seen before, but we go over it. So section 3.6, it's derivative as, okay, the section is called derivative as a rate of change. But today we will emphasize again the derivative as a velocity because it's crucial. All right, so let us see what is the setup in those scenarios. The setup, so we have an object moving along a line. So suppose we have an object moving along a line. Vertical or horizontal, it doesn't matter, with a specific direction. So usually you will be told whether it's the object moving to the right is the positive direction or going up is the positive direction. So an object moving on a line with a very specific direction, with a given direction. Vertical, horizontal, up, down, with a given direction. Okay. And we have a function which tells me what is the object at every moment in time. So S of t is the position function. It means a function that gives the position with respect to a reference point. A function that gives the position with respect to a reference point. With respect to a reference point. Okay. So first we just remind you of the definition and then we work out a problem. Now the displacement of the object or the change in position. So the displacement of the object for t between two time interval or change of position which is denoted by delta S, is defined to be the position at B minus the position at A. So that's what we call the change in position that we talked about it before. But what I want to talk about is that when I'm talking about the change of position, it's always the position at the right value at the larger value minus the position at the smaller value. So when we're thinking about time, we always, or input, we always go from left to right. So it's the value at B minus the value at A. And it's important because a lot of us are function after function given, function that gives position with respect to. Okay, so this read with respect, okay, to a reference point, with respect to a reference point. So we have a reference point that we are working with it, because I have to tell you where the object is, but from where. So like when I take a rock and we throw it up, the reference point that I see could be the ground level. So I will tell you where is the position with respect to the ground level. Ground level is actually the reference point. So the displacement or the change of position is given by that. So that's, so the average velocity for t between A and B, so these are things we've seen, is the displacement divided by the change in time. Okay. And finally, the instantaneous velocity. It means the velocity at a given moment in time. So the velocity, or sometimes that's called instantaneous velocity, is at a specific moment in time. What is the velocity? We do the following. We take the average over a small period of time. Now the period of time, we call it h. So that's represent a very small period of time. So we compute the average between t and t plus a little bit. We divide it by the time. So that's the average. That's displacement over time. And we ask ourselves, as we take the average over a smaller interval of time, that's what we mean by the instantaneous velocity. And another way to write this, another way is the change of position over the change in time, because h is the change in time. And sometimes instead of writing h, we say when the change in time become very small. So this is nothing more than derivative of the position with respect to time. So that's the instantaneous velocity. And graphically is the slope of the tangent line. Okay, so this everything here, we basically saw it. So that was our main application for the derivative in physics, is that if I know the position function, its derivative is actually the velocity at a given point. Okay, so we're going to have a small problem related to that, and then we're going to talk about the idea of acceleration in terms of application of the derivative. Okay, so let's start a problem that we actually done something fairly similar before, but we repeat it. Okay, so here's my example right there. Now, suppose an object is moving and I'm giving you the formula for the position. It means in my mind, so S of t is t squared minus 4t plus 3. That's the position function. And let us say t is in feet. Sorry, S of t is in feet and t is in minute. Okay, so first question, we're going to graph the positions. So question number 1, graph the position function. So we somehow interact with it. Graph S of t, the position. All right. So how can we graph it? Let's see here. We're going to graph it. So that's S of t. And that's a parabola. Now we can of course use the graphing device, but this is a parabola going up. At t equal to 0, I am at +3. That's what it is. And we know it's a parabola going like this. And let's see, when does it hit here? Let me see if I can find its zeros equal to 0. And I'm just finding when it's going to intersect. So I'm setting it equal to 0. I'll get 3 and 1, t and t, and I will have minus and minus. So t equal to 1, it hits, and t equal to 3. So this seems to be going like that. That's really how the graph, that's S of t. Okay, that's time, and that's S of t. Now, can we find this point easily? Can we find this point easily? Who can give me this point without getting into a calculator? Who can give me this point? We should be able to. Who can give me the coordinate of this point? What this point should be? 2 minus 1. Either by symmetry or what happened at this point. So if I want to find this point, I say, you know, this is where the derivative is equal to 0. That's where the slope is horizontal. So I take the derivative right there, and I set it equal to 0. So it is basically when the velocity equal to 0. So I would get 2t minus 4 equal to 0, t equal to 2. Okay, so we don't even need a calculator here. We know that it bottoms up when the derivative is 0. So this point is 2. Now I want the output. If I plug in 2 in here, I'll get 4 minus 8 minus 4 plus 3 would get a minus 1. So Elizabeth is absolutely correct. All right, so this is the graph of the position. Now we want to describe the motion. So now describe the motion. It means describe the motion a little bit. Okay, so what do I mean by that? This function tells me at every moment in time where my object is. So it means here, just so that's a small table to help us. It means at t equal, that's time and that's the position. So at t equal to 0, when the object started moving, it was 3 units from its reference point. That's really what it is. Now, after 1 minute, the object is 0 units from its reference point. After 2 units, the object is minus 1 unit from its reference point. After 3, it's back to its reference point. And after 4, we don't care, we just plug it in here. So after 4, so if I take t equal to 4, where is my object? And we should get 3. I will have 16 minus 12. 16 minus 12, which is going to give me a 4. 4 plus 3, we are back at 7. Okay, so these are some value. Now describe the motion. Let us remember that the object is moving along a line. That's where my object is. Okay, and this is give me where it is with respect to a reference point. So let me call this my reference point. So everything, all those are with respect to that. And going to the right is the positive direction. So that's the line of motion, and that's my direction. Okay. And now let us exactly describe where this object, so that's where it's moving. And this gives me information about the position. So initially at t equal to 0, my object is 3 units away. So this is S of 0 basically. So at t equal to 0, my object is right here. That's where my object at t equal to 0. So we can put here a little bit t equal to 0. Okay, so it's right there. And then what my object is doing. Is it moving to the right or moving to the left? Back to you. But we have to understand the position function. What is S of t doing? Right or left? What can you say? Initially, it's 3 units from this reference point. And then what's the object doing? Is it heading? I don't know. You guys tell me. Left or right? What do you think? Right, left. Oh, I'm getting those answers. Not going to work. Left, right. Why? Because what is the object doing? S of t is 3, but then S of t is getting smaller. and smaller. So its position with respect to the reference point is getting smaller in the sense that it's getting closer and closer and closer to its reference point. So at t equal to 0 is here, but at t equal to 1, my object is back at the reference point. My object is right here at t equal to 1. So between 0 and 3, it seems to have moved this way. So S is actually decreasing. That's S. This is where the position is actually decreasing. So we are right here at t equal to 1. And then what is doing? Between 1 and 2, so from here to here, what's my object doing? So I'm thoughtfully studying the motion. Is it keeping to the left or moving to the right? What can you say? So what is S here? S is negative. It's keeping left. S is, don't be afraid of the negative. S is negative. S is negative. So if this is 0, negative, it means we're right there. So it means that my object now is staying away, is moving farther away from the position, but to the left. So it's moving farther away, farther away. So this is -1 here. And this is t equal to 2. So my object is right here at t equal to 2, but it's moving, that's -1. So that's my reference. So it's moved to the, it starts here, it's moving to the left till -1. And then what's my object doing? Between 2 and 3. What is it doing? This is S. It means that's its position. So it's negative, the position is here. And then its position seems to be getting less negative, heading toward the reference point. So it's right there, but then the object is actually start to head back toward this reference point. And at t equal to 3, it's back right there at its reference point. Now it's moving to the right. Now the object is moving to the right. And after that, it's moving away from its reference point. So the object then takes off and keep moving this way. So that's really from the position function. That's the motion of the particle at hand. Okay, so it starts as S of t is decreasing, or S of t heading toward its, basically decreasing or heading toward its reference point, the object moves to the left. It keeps moving. It passes the reference point to the left, and then it starts moving forward and forward and forward. Okay, so that's really that. So that's the motion. That's where the object is, and that's really the motion of the object. Now, a little bit about the displacement. So suppose I ask you, find the displacement. Find the displacement or the change in position. Find displacement or change its position between t equal to 0 and t equal to 1. Okay, or let us say t equal to 2. So find the displacement between the time t equal to 0 and the time t equal to 2, the object moved, displaced. So at t equal to 0, it was right here. At t equal to 1, sorry, at t equal to 2, the object was right here. But this is by how much was the object displaced between 0 and 1 and 2, by how much it was displaced. And the displacement is always equal. That's a mistake you did on the quiz. It's always the value at 2, at the higher value, because we move from left to right. So it's S of 2 minus S of 0. It's not the other way around. It's S of 2 minus S of 0. That's the displacement. Now, what is S of 2 minus S of 0? Okay, S of 2 is -1, if we plug it in, minus S of 0 is 3. So that's -1 minus 3, which is -4. Watch the negative sign. Okay, so it means between t equal to 0 and t equal to 2, the object was displaced. But by how much? By -4. It means the object was here and it moved in the negative direction, or to the left by 4 units. And that's important, the -4, because it's telling me how the object is moving, the direction in which it's moving. So it moved by 4 units. That's what the picture is really telling me. Okay, but it moved because at 0 we here this is a 3 in here. So from here to here we have 3. So it moved by 4 units, but the -4 is telling me that it moved actually to the left. So the displacement tells me you start from here, move 4 units to the left, and that's where the object is. Another word for displacement is actually the change of position. It means the position changed by 4 to the left. Okay. Now let us find another displacement. So let us find displacement between, let us say t equal to 0 and t equal to 3. Okay, what's the displacement? I apply the formula verbatim. It's s at 3 minus s at 0. And then we visualize it here. S of 3 is 3. We plug S of 0, no, my apology. S of 3 is, we picked up some values here. It's a 0 minus. S of 0 is 3. The answer is -3. Let us understand this -3, what it means. At t equal to 0, the object was here. At t equal to 3, the object was right there. So from 0, time t equal to 0 and time t equal to 3, the object was displaced by 3 units. So it's not the distance that it traveled. It's actually by how much it was displaced. So the object was here, it was displaced. It means this is the position, then the position was here. So the position was here. After 3 minutes, the position's here. It means it was displaced by 3 units to the left. It's not the distance it's traveled. It's just by how much it was displaced, by how much the position changes. So suppose now I ask you find the distance traveled. What will be your answer? Sorry. I say it in words. Suppose the question is find the distance traveled. The distance traveled between t equal to 0 and t equal to 3. What would be your answer? Look at the picture. Totally the picture. How much, what's the distance traveled? Not the displacement. Object was here at 0. The object was here at 3. We look at the picture. What's the distance it traveled? Let's look at the picture. The object was here. Moves back here. What's the distance it traveled? Five. Do you agree? 35? Where did you get 35 from, Elizabeth? 5. Absolutely. It was here at 3 units. It moves 3 up to here. 1, 1. The distance is 5 feet, whatever the unit is. But the displacement is not usually the distance, it's by how much the position changed. The object was here, it was here, so it was displaced by 3 units, but he traveled more because he went backward. That's why we lost this piece. Okay. So that's the displacement. So by how much the object changed position. That's really what the displacement is. Now, the rest is going to be back to find the, so that's the motion. So question number 2 is find the average velocity. Find the average velocity for t between 0 and 2. Find the average velocity. Okay, what's the average velocity? The average velocity is nothing more than the displacement divided by time. Displacement over time. So the displacement is S of 2, which is going to give me -4/2, which is -2. The minus is important. You don't really let it go. The minus tells me that my object between 0 and 2, so that's feet per minute here, This tells me that my object between the time t equal to 0 and the time averaged 2 feet per second, but going to the left. So this tells me that's going to the left, and that's it averaged 2 feet per minute. Okay. Now, question number 3 is find the velocity at t equal to 2. Now the question totally changed. Find the velocity at t equal to 2. Not the average velocity. It means we know that the velocity is changing. So between 0 and 2, it averaged 2 feet per minute. But the velocity is actually changing. When you take an object and the object is moving, the velocity changes. Now I want the exact velocity at t equal to 2. So let us see what's the velocity. The velocity that we usually is the derivative of the position function. Now, this is my position. It's t squared minus 4t plus 3. So the velocity is nothing more than the derivative, which is 2t minus 4. So at t equal to 2, the velocity is, I plug in 2 in here, which is equal to 0. Did I expect that in the problem? Did I expect the velocity to be 0 at t equal to 2? Yes or no? What do you think? Let's watch the graph. Absolutely, watch the graph. So the object was moving. The slope of the tangent line here is 0. So basically the object moved and it had to turn. So the velocity basically decreased. So for it to be able to turn, it's just like stopped a little bit and then move backward. So that's where the velocity is equal to 0. Now find the velocity at t equal to 1. After 1 minute. So the velocity would just graph. So velocity at 1, I plug in 1 into the expression. It's 2 times 1 minus 4, which is happen to be minus 2 feet per second. Now, why the velocity is negative in this problem? Let's go back to the question. So after 1 second, it means when t equal to 1, if we look at the graph, I'm finding the velocity. It means I'm finding the slope to tangent line, basically. So we expect that the velocity to be negative because the slope is negative. That's interpreting the velocity as the slope. Another reason why we expect the velocity to be negative, because at t equal to 1, we know that the object is going in the opposite, in the negative direction. That's also what caused the velocity to be negative. Because in here, all those average velocity are going to be negative. So the instantaneous will be negative as well. Okay. Now we're going to talk a little bit about what's the acceleration. Okay. What's the acceleration? Okay, I'll ask you a question before I tell you what the acceleration is. When you say that you're accelerating, what do we mean by that? When we say we're accelerating, it means what's changing when you're accelerating? The speed is changing. Okay, so velocity, the velocity tells you that if your velocity is high, it means your distance is changing a lot with time. That's what the velocity represents. How fast is the distance changing? So if you're driving a car and your velocity is like 80 miles per hour, it means your distance is changing a lot with respect to time. The acceleration measures how much the velocity changes with time. It has nothing to do with the distance. It means your velocity is changing. So suppose I give you the following table. This is time and this is velocity. And I link up sometimes. I tell you, okay, so at t equal to 0, your velocity was 0. At t equal to 3, your velocity is 20. At t equal to 6, your velocity, for example, was 33. So that's meter per second and per second. And then your velocity is 43. So here, I'm giving you how the velocity is changing with time. So it was 0. 20, 33, 43. And suppose I ask you find weird question. What's the derivative of the velocity? It means how much is the velocity changing? Okay, what's the derivative? This is a weird question. I've never asked you a question like that. So the velocity, the derivative is you take the change over how much the velocity changing, so the change of the function over the change of the input. Now in this problem, I don't have a formula and I don't have anything. So if I want to take 0 plus h minus v of 0 over h, the smaller h I have, so the smaller h here is actually 3 because I don't have any other input. So in this problem, what's the derivative at 0? So a derivative at 0 here is going to be basically, in this particular problem, because I don't have much data, v of 3 divided by 3. Means in this particular problem, it's going to be that, which is 20 minus 0, which is going to give me a 1, get a 2, I get, sorry, it's a 6.6, almost. Okay, so if I tell you what's the derivative here of the velocity at 0, you say, okay, it's nothing more than, so that's the graph of the velocity is, I don't have data, so the only thing I can work with is with this little table I'm giving you. So it's nothing more than the change here, so that's the change up here, over the change in here, which is gonna give me 6.6. But that's, what's the unit in this scenario? What's the unit? This here is feet per second. I meant meter per second. The unit here is a second. It means that my unit here is going to be meter per second per second. So if I give you the velocity and I tell you what's the derivative of the velocity, is basically I'm asking you how fast is the velocity changing with time. So this is telling me that around initially the velocity is changing, the velocity is changing. So it's this measure of the velocity. So at t equal to 0, the velocity is changing at the rate of 6.6 meter per second per second. So that's how much the velocity is changing. We call this the acceleration. So the derivative of the velocity, we're going to call it acceleration because it's going to measure how fast the velocity is changing with time. So the acceleration is not a change, it's just how fast the velocity is changing. So the acceleration, so suppose s of t is a position function, then the acceleration is the change of the velocity at time t, which we usually denote by a of t. A of t is defined to be the change of the velocity over the change in time. So if velocity over time. And now if I have a lot of data, when the change in time becomes very small. So the acceleration is how fast the velocity is changing with time. But this is nothing more than the derivative of the velocity. Okay, so the acceleration is nothing more than the derivative of the velocity. So we can write it as dv dt, the change of velocity with respect to time. Okay, so I have to stop at this moment, and tomorrow I have 2 extra words to say about the acceleration, and then we move on to a new technique. Okay, any questions before I let you go? Any questions? All right, so see you in my office hours in case you guys have any problems, and I will end the meeting. See you tomorrow.